On Friday, though, we've made it.
That is true.
What is it? Not, I mean, no.
That's interesting. Well, no, my I think all my stuff just there we go. Maybe. You're gonna go, everybody. Yes. That end. That okay, good. There we go. All right. It's Friday. We've made it. Just got to get through the day. It'll all be okay. I'm exhausted also. Let's start with questions. Do you guys have anything that you want to talk about from homeworks? Mackenzie? 2.6, which number? 33. Okay. So the limit as x approaches infinity of arctan e to the x? Okay. Okay. And remember, what does arctan mean? It's been a while since we've encountered that, and we usually don't write it in that fashion. It is the same thing as tan inverse, or we can treat it the same way as tan inverse anyways. Very good. Yeah, okay. So the way I'm going to think about this is I would be thinking about it kind of in this fashion, right? And what is the limit as x approaches infinity of e to the x going to be? Well, what's the graph of e to the x look like? Right? It's an exponential function, so it's going to look like this. As x goes to infinity, e to the x goes to infinity, right? Everybody's okay with that? And in fact, it's going to infinity really fast because it's an exponential function. It's like your fastest growing function type. Okay. So really the way I'm going to think about this then is I'm going to make a dummy variable for the inside. I'm going to call that dummy variable t. Because really what I'm looking for is then the limit as arctan, or the limit as t approaches infinity of arctan t. Where I've just taken the inside guts that I know is going to infinity, just put a dummy variable in t where the limit for t is going to the same thing that the limit as x approaches infinity of e to the x was. Everybody's okay with that idea? All right. Now, how am I going to evaluate this? So you could look at the graph. You could make a table. Both of those would be good options here. There's not a good algebraic way to do this. So let's just fire up the calculator and take a look at the graph. That's probably the best place to start. And then we'll do a zoom trig on this. Oh, I probably need to be in radian mode since I didn't get anything. Okay. So this value here is the value of e to the x as x is getting bigger. What do you notice that value, y value, is looking like? 1.5 and change should speak to us. Pi over 2. And I think that if we think back about what the graph of tangent looks like, we have a vertical asymptote at pi over 2, where tangent is going to positive infinity at pi over 2. So if tan inverse of x is going to infinity, then it should be outputting the angle measure pi over 2 there, right? You could think about it that way as well and have not needed the graph or your calculator to do that. You could have done it intuitively from what you know about the graph of tangent. But that's maybe a big ask for still the first month of school. It's a big pull from last year. You know what I mean? Mackenzie, are you happy with what we did there?
Yeah.
Okay. You don't sound happy.
No, I
Okay. Victoria?
I see how you graph.
Number 9 and also in 2.9 or 2.6, excuse me. Okay. So it says that we have a bunch of things. We have f of 0 is equal to 3, and then we have a bunch of limits, right? So the limit as x approaches 0 from the left is 4. And the limit as x approaches 0 from the right is 2. And the limit as x approaches negative infinity is negative infinity. And the limit as x approaches 4 from the left, is negative infinity. And the limit as x approaches 4 from the right is positive infinity. And then the limit as x approaches infinity is 3. Okay, that's a whole bunch of stuff to account for, but that's fine. We can handle this. So let's see. F of 0 equal to 3 just means I have the point 30. It has to be in my function. And then the limit as x approaches 0 from the left is 4. So it's doing something like that. And the limit as it approaches 0 from the right is 2. So I'd have to be doing something like that. So far, so good?
yeah. Why? Like, you know how when 2 went up and like the 4 went down, does it matter?
I'm just guessing.
Okay.
Just guessing.
Okay.
If I decide that, nope, this should be going the other way, I can just, make them start going the other way. I'm going to ignore these guys for now, since those are the very ends. I'll do those last, since those are when x is approaching positive and negative infinities, and worry about the insides here. Now I have 4 where our both of those limits are going to infinity. What does that mean is happening at 4? That's the definition of a vertical asymptote. So I'll draw that asymptote in. And then from the left, it should be going to negative infinity. So I guess we'll just loop this piece down. And from the top, or from the other side, it's going to positive infinity. So far, so good, Victoria?
Yeah.
Okay. And then my last piece are now these guys here. And these are horizontal asymptotes, assuming they're finite. So I'll do this one first. As x approaches negative infinity, the function goes to negative infinity. So this is just like shooting straight down. And this one, it says as x approaches positive infinity, the function's approaching 3. So that's like a horizontal asymptote. So it should look kind of like that. And again, does it have to look exactly like mine looked? No. And in fact, on hindsight, I would probably go and like redraw this part so it doesn't cross that asymptote, but it doesn't really matter. You know what I mean? That middle piece doesn't really need to cross it, so why would I have it crossing? But, you know, otherwise, if on something like this, they're just checking to make sure it satisfies the key features that you've given. If it's doing something weird in between them, that they're like, oh, why did they do that? As long as it's doing the key features, you're fine. So like lots and lots and lots of answers possible here. Everybody's graph should look kind of the same, but not totally identical. Does that feel good?
Yeah.
Okay. 27. Sure. So here we have the limit as x approaches infinity of the square root of x squared plus ax minus the square root of x squared plus bx. Okay. First things first, if I try to do this as a direct substitution, what am I going to end up with? I'm going to end up with infinity minus infinity, which is indeterminate. That's not 0. That's one of those indeterminate forms. Remember, there's 7 of those, like infinity over infinity, or infinity minus infinity, or 0 times infinity, or 1 to the infinity, or 0 to the infinity, or, I'm sorry, infinity to the 0. These are all these like indeterminate forms where it's like, you can't do anything with this. You have to just try something else. Okay with that, Victoria? Okay, so hopefully what to try next should be kind of obvious based on the form of this. You'd want to multiply by the conjugate, I'd hope. Would be the, hopefully is the obvious trick. Okay, so when I do that, I'm going to get x squared plus ax minus x squared plus bx. Got to be careful with the parenthesis there. Victoria, you happy with what I've written there? You see the simplifying? Okay. So if I do that, I'm going to have ax minus bx on top. And then x squared plus ax plus square root x squared plus bx on bottom. And then I think here I'm going to multiply the top and bottom by 1 over x there.
Why is it the minus?
Well, the denominator is still 1 over x, right?
Yeah.
I've just written it differently because I need to multiply it into the square roots.
Okay.
So it has to be under a square root to do that.
Oh, so like the square root and two cancel out.
Right.
Okay.
Yeah. So again, I want to point out to you, actually, let's take a second before we do that. If I tried to direct substitute in here again, notice that the numerator is still infinity minus infinity. So that's why I'm continuing to go.
Yeah.
Why I didn't stop here and try to direct substitute. I didn't mention that, but I probably should have. So let's take a moment, just recognize that we're still in a bad spot. Oh, excuse me. That's not right. That's a 1 there. Kulik, come on. There you go. Okay. Now, yes. Well, 1 over x squared times x squared should just be 1. I just was thinking about it still as 1 over x instead of what I'd written down there, so I just goobered it. Ever do that? Yeah. All right. So now I can think about these as separate parts. So I can do like the limit of the top divided by, and then I can kind of push that limit through to all the different pieces in the bottom. Everybody's okay with that? So the limit on the top is, limit of a constant is just a constant, so a minus b. And then the limit as x approaches infinity of 1 is 1. The limit as x approaches infinity of a over x, 0, right? You have a over big, that goes to 0. And then similarly, the other piece I'm going to have also 1 plus 0. So that's going to simplify down to just a minus b over 2. Victoria, doing okay?
Yeah.
So again, multiplying by the conjugate, absolutely the correct first step. That's probably what you want to do. The issue then was,
No, maybe just knowing when to divide by the 1 over.
yeah,
I didn't know if I should do like start.
I'd probably wait till I had a fraction.
Okay. Did you do it when it started?
I don't think it would help.
Okay.
I mean, you could, but then you'd end up with 1 plus a over x plus 1 plus b over x, or I'm sorry, minus the 1 plus b over, and then 1 over x squared in the denominator, and when you try to do the limit, your denominator is going to 0. So you're still like in a dumb place, kind of thing, you know what I mean?
Yeah.
I don't think you can get away with doing it without the conjugate first. Mackenzie? 37 from the same section, I assume? Okay. Limit as x approaches infinity of e to the negative 2x times cosine x. Okay. Oh, this is lovely. I would do this as I would start by separating this into the product. Okay with that? And then it should be pretty clear that this first limit is 0. Well, remember we had this proposition from last time? Right, that was one of our propositions. And obviously if it's true for 1x, it's going to be true for 2x because it's just... And the reason I think about that, the other way you can think about it is that this is just the same thing as, right? So you have like 1 over big, that's going to 0, right? And then cosine, I know, is bounded between what two values? This is trig. -1 and 1, right? The important piece there is recognizing that that is not infinite, because 0 times infinity is one of the indeterminate forms. I don't have that here, though. I have 0 times something finite. I'm just going to write finite here. So that's just 0. The piece that I need to have there, though, is need to recognize that the limit as x approaches infinity of cosine is not infinite, right? Now, I can't say what it is because cosine just oscillates back and forth. So I don't know what the limit is. In fact, the limit doesn't exist there. But that's okay because it's finite still. And 0 times something finite is going to be 0. Mackenzie, is that?
Yeah, that makes sense.
Okay. So again, little tricky there because there wasn't a way to do that limit piece at the end to actually get a number or value or whatever. Victoria?
If you just knew that the first was 0 and 0 multiplied by x, could you just put your answer?
No, because again, when we think about the indeterminate forms, 0 times infinity is one of the indeterminate forms. So you really had to be careful there and make sure that that other piece wasn't 0. So you did have to think about that other piece a little bit. Now, you didn't actually need the value that that limit comes out to, but you did need to make sure that it wasn't infinite. Does that, you feel okay there?
Yeah.
Like it makes sense when I explain it to you, but it's like, why is it finite? Well, if I look at the graph of cosine, right, what's it look like? It's going to be doing this.
Yeah.
So at no point does the value of cosine ever go to infinity. It's always stuck between -1 and +1. So I know that even though I don't know what that limit is, in fact, the limit doesn't exist, I do know that it's a finite number.
Oh, okay, so that's just something that you just know.
From trig last year. Yeah. Yeah. And again, if you, when in doubt, you could have graphed cosine on your calculator and looked at what was going on, and you would have seen the values of cosine are all stuck between -1 and +1. No matter how big the x is getting, they're just hanging out there. You know what I mean? Okay. Should we start 2-7? It's time. It's time. Hey, look, we've done a bunch of examples, right? And I don't mind doing that.
No. Oh.
Okay.
It's really scary.
today we're going to begin to the introduction to the derivative. That'll be there's two kind of fundamental calculus operations that we're going to study in this course. They are the derivative and the integral. We're going to spend most of first semester working on derivative pieces from here on out. So we'll define what a derivative is here. We'll talk about some of the ways to calculate a derivative. We'll develop all kinds of different shortcuts and methods depending on what your function looks like, on how to do this. We'll look at applications that we can use where derivatives come in handy for like real world problems. And we're going to do all of that here in first semester. Second semester, we'll get into integration. And then that'll be, well, maybe at the very end of first semester, we'll start integration or start that idea. Okay? All right. So let's start with some definitions here.
Yeah, Mr. Cook, what's RFC?
Oh, rate of change. All right, so we did a little bit of this very long ago, way back in the very beginning of chapter 2. So we're going to define here the tangent line to a curve at some point as the line through that point that also has the slope limit as x approaches a of f of x minus f of a over x minus a. Looks like the slope formula, right? Change in y's over change in x. So let's just do a little quick example. So let's find the tangent line to y equals x squared at the point 1, 1. So to write the equation of the line, I need a point and a slope. I have a point here, 1, 1. What I need to do is calculate the slope. So to do that, I'm going to use that definition above. So the limit as x approaches, what is a in this case? 1, the x coordinate of the point that I'm looking at. And what is f of 1 in this case? Also 1. And what's f of x in this case? X squared, right?
Oh.
Oops. Is everybody cool with how I filled that in? Can I evaluate that limit by direct substitution? No. What do I need to do first? I could factor that and then try to reduce. That should be the obvious thing you'd try. Once I've done that, now I can do direct substitution, and I have that my limit is 2. I'm going to use the point slope equation for a line to write my equation for the line. That's the point slope equation. I like to use the point slope equation in cases where I'm given a point and a slope. Tends to be quite convenient. And then I just rearrange to get my slope-intercept standard form equation for a line, or my slope-intercept equation for line. Everybody's okay with that? Looks familiar, right? Sophia? Stretch? Okay. No problem. All right. So another way to think about this is if we have some function f of x, we want to talk about the point that's quite close to f of x. What are we really doing here? It's basically looking at the instantaneous slope, right? The slope at a single point, because these 2 points, the difference between them is going to 0. Right? H is the difference between the 2 points. That's basically going to 0. So again, this is like our instantaneous slope. It's the same thing as the slope of the tangent line. It's just a different way of writing it. So let's do another numeric example here, just using this notation. So let's say our function is 3 over x, and our point is 3, 1. And again, we're looking for the tangent line here. So what we need is the slope.
So for this form, it's always x or h or whatever approaches.
It's always h approaches 0. Yes, that's why this is going to become the preferred form, because it doesn't ever change. It's always h going to 0, which is nice, as opposed to the other one where you have to think about like what a is and make sure the limit's going to the correct place. Okay, so if we continue kind of going through this, what is f of 3 plus h going to be? Means that I'm going to plug in 3 plus h to x in my f of x, right? So it's going to be 3 over 3 plus h. What's f of 3? Is 1. Everybody's cool? Yes.
In that equation?
Oops, that's minus.
Yeah.
Thank you. Thank you. All right. If I try to do direct substitution at this point, what's going to happen? I get 0 over 0, which is bad news bears, right? So what should I do? I would make a common denominator in the numerator and see what I can do with that. Right? Those are two things that could be added together that maybe some stuff will cancel out if I do that. So that common denominator just would be 3 plus h. Oops, I did it again. It's a subtraction symbol. What do you notice happens in the numerator? What do I get when I subtract those two fractions?
No, that's wrong.
Well, I know the denominator is 3 plus h, right? Oops. Mr. Kulik got to remember to write that. It's, well, this spot is not h. What's that numerator up there that I haven't written in yet? It's not h. Negative h, yes. Remember the negative sign has to distribute through?
Yes.
But that's really great, because if I think about that now as the division of two fractions, I can think about that as the limit of negative 8, or as h goes to 0, of negative h times 3, or over 3 plus h times 1 over h. Let's not going to do it again. So when I do my direct substitution, that's going to be negative 1 over 3 plus 0, or negative 1/3. Sophia.
So if you're doing direct substitution, that's
After I've got rid of the h's, yes. I just didn't want to write the limit again with the reduced form, because it's like,
valid.
you can see, everybody can see what I did there. I think at this level you guys can see, right, that at least with the narrative to go along with it on how I did that. All right, so point slope time. Oops, I put those things in the wrong spot, didn't I? X was 3 and Y was 1. My apologies. And then I just need to simplify things out. Two. All right. So remember where we started this discussion way back on the first day? Calculus was developed by Newton was one of the co-developers in an effort to do what? Deal with gravity, right? Wanting to calculate the instantaneous speed of a falling object. So the relationship between position, and I'm going to put in instantaneous velocity, and then acceleration. And maybe we'll put instantaneous here. What's going on here? So if I have like some position function, I'm going to have like distance on one axis and then like time on the other, right? Everybody kind of agree with that? And say that my position function looks like this, where I've like thrown an object straight up in the air and then it's come back down on the ground. If I want a graph of its instantaneous velocities, what is that going to be? Well, it's going to be like each point t is going to have the slope of the tangent line at that point, right? Let's label that position. So instead of distance over time, these are going to be velocities. These are going to be rates, distance per times at each unit time. Oh, excuse me. It'll be like this, actually. Oh, sorry. Like this. Yeah, like that. And acceleration, what is acceleration? It's the rate of change in speed or velocity, right? What do you notice if I draw a tangent line to my velocity graph? What do you guys notice? Any tangent line I draw is the exact same, right? Oops. So my acceleration graph is the rate of change. So it's like the distance per time, or just per time squared. And what's that look like? Here, for an acceleration graph, would just be like a straight horizontal line, right? Since the slope is negative, I drew in one with a negative value. Okay, so velocity is the rate of change in position. Acceleration is the rate of change in velocity. Everybody feel okay with that? So, if we have, if f of x is our position function, and we want the instantaneous velocity at some point a comma f of a, what is the velocity at that time? What do you notice? It's the exact same formula, right? Ooh, that's handy. And you could go forward and even say then, like, if f of x is a velocity function, and we're talking about the point a comma f of a, the acceleration at time a is going to be the same thing, right? Ooh. So this like calculation of an instantaneous rate of change, we're going to give a name. We're going to call it the derivative. So this definition is the derivative of a function at a number, and I'm going to use the number a. Maybe I'll do that so it doesn't look like bad grammar. Okay, and our first notation that we're going to use to denote a derivative for f is I'm just going to put f prime. So that's like an apostrophe, not a number one, but it looks, when I write it, it's going to look just like the number one. In the text, it'll be easier to see that it's like an apostrophe or whatever. What do you suppose this formula is? The same thing we've seen now several times. Oops. If I can write it, Mr. Kulik. Everybody's okay with that idea? Alternatively, how else could we have written this? Remember, there was kind of two ways to describe the slope of the tangent line. There's going to be two ways to kind of do this. The less common way we would write this is that other slope of the tangent line. But this one we almost never use. Yes? Someone, Mr. Kulik, me? Search. Here's what we don't like, is that this is going to change depending on the point. This never changes depending on the point. That's why we like one versus the other. But it's really like a matter of style, but you're going to see that the first form is actually going to be better because we can generalize from there a little bit easier. Because in the next section, we're going to stop talking about the derivative at a specific point and just talk about the derivative of a function in general. And that's where the upper formula becomes massively easier to deal with. So that's why. But yeah, I mean, the second one is a little bit more clear as to like what's going on. Notationally, like you can see exactly what's happening. Okay, as the x is getting closer to the point in question. Okay. So we have that. How can we update our tangent line definition then? The tangent line to f of x at the point a comma f of a is the line through that point with slope equal to f prime of a, right? We saw that the slope of the tangent line definition was the same as our derivative definition, so we can just say the slope is going to be the same as the derivative of f at a. Just saying the same thing over and over again, right? Let's do an example. Okay. Look at that national debt. Just the climbing. Is there a website for this where they show you like the national debt just like going like $1 million in that, like a minute or whatever that we're burning? It's pretty scary looking.
It's like in the trillions, huh?
Yeah. I mean, it was trillions here because these are in billions of dollars. So
10,000 billion trillion.
yes, yeah. Well, 1,000 billion is a trillion.
Right.
Yeah. All right. So if I want to estimate for the value of d prime of 2,000, what would I do? I would want the slope of these two and then average them together. That'll be a reasonable estimate for the rate of change of debt in the year 2000. We'll take the average rate of change from 1995 to 2000 and the average rate of change from 2000 to 2005, and then take the average of those two. You guys buy that? Does this sound exactly like the kind of thing we're doing in like 2.1 and 2.2? Yes, it's all the way back, Taylor. I'm sorry.
What are we estimating? Like, it says estimated, but there's, like, are we estimating the slope of it?
So d prime is the derivative of our function d in the year 2000. The derivative is the rate of change. So ideally, we want the instantaneous rate of change. Can we get that from a table, though? No. So that's why it says estimate. So we're going to take the average rate of change from 95 to 2000, along with 2000 to 2005, and then average those guys together.
Okay.
Does that feel okay?
Yeah.
Okay. So if I want the slope from 95 to 2000, well, that's quite easy. So I get like 134.70. If I want the slope from 2000 to 2005, that's going to be 8170.4 minus 5662.2 divided by 5. And that's about 501.64. And then I'll say that d prime of 2000 then is approximately 134.70 plus 501.64 divided by 2, which rounds to about 318. And what unit should I have on this? What are these numbers? What's the unit on these numbers? Billions of dollars. And then since it's a derivative, it's a rate per year. Okay? So you might say that in the year 2000, the national debt is increasing by $318 billion per year. Woo! Spend some money, guys. What is this? 27.
Are you done?
Oh yeah, there's no way.
This is that section. We're going to start 2.8 though, because this is a rather minor section.
This isn't due Sunday, is it?
Correct. This is not part of Sunday's problem set. Sunday's problem set is just, what, 2.5 and 2.6? Sounds right? Yes, Taylor.
For that last problem, is that 318 the answer?
Yeah.
It is?
Yeah.
We didn't use the equation.
Because we didn't have a function. We didn't have a function defined to use the equation. We had just the table of values that described our function. So we had to use the table to make an estimate rather than finding out exactly, because we didn't have like f of x equals some function.
Okay.
Is that,
Yeah. It just seems simple and then it should be.
Oh,
this section should be very reminiscent of like 2.1 and 2.2. I think it is probably like the second or third easiest section in the in this chapter, and maybe even the easiest based on what you've done before, that there's nothing really new. We're just kind of giving stuff that we've done a proper name to it and using the limit notation a little bit heavier, but it basically boils down to just doing slopes. Okay. All right. So this next section is about the derivative as a function. Rather than the derivative just being a value at a specific point, we're going to talk about the derivative as a function. So we have the derivative at a point. We did that just a moment ago. Right? Now, what happens if we don't want to do this for a specific value of a, but we want to do this kind of in general? So if we let a vary, so what do we do when we let something vary? We use a variable. The variable I'm going to use in place of a is going to be, shocker here, guys, x. So this is going to be the derivative of the function f of x. I feel like I didn't write that down correctly. Let me look real quick. Oh, they didn't give this a special. Okay. Okay, so let's say that this is our function f of x. And I'm going to try to sketch on the same set of axes the graph of the derivative. The first thing I'm going to do when I want to do something like this is I'm going to identify the places where my function has slope 0. How many places on this do you see where the slope is 0? Should be 3. What are the 3 points?
It's like
The extrema, right? So when I'm drawing my derivative, I know it's got to have x-intercepts at those 3 same x values. Everybody's cool with that? Now I'm just going to kind of sketch to collect this together. So on this section, the slope is positive, negative, negative. So my derivative should be below the y-axis there. Right? What happens in this section? It's positive, and notice the slope goes from increasing to decreasing, like it's getting from steep it's less steep, steep in the middle, less steep again. So it's going to be coming up from the x-axis and then going like back down. Probably steeper than that though, huh? Like that. Everybody's okay there? Look at the next section. Slope there is negative. And so we'll just, oops. And the last piece has slope positive, so I don't know, something like that. Everybody's cool? By and large, what would the grader be looking for on a problem like this? They want to make sure that your x-intercepts are in the correct place, and that the graph is on the correct side of the x-axis. That you've labeled the parts with positive slope above the x-axis and the parts with negative slope below the x-axis. But there's not much to do. How high you want to make the extrema on your derivative, you can't really say very well without really putting a ton of work in. That's not necessary for a problem like this if we're just sketching. Okay? Does that feel okay? All right. Let's do one more example and we'll quit today. All right. So we're going to find that derivative of f okay. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. That's just our definition, right? Let's start filling stuff in. What is f of x plus h going to be? X plus h cubed. And then f of x is just... Ooh. No, that's not right, Mr. Kulik. Everybody's okay with what we did there? Okay. What should Mr. Kulik do next? I plugged x plus h into f. That gives me those pieces. And then f of x I plugged in, and that gave me that piece. It's like a composition of functions from Algebra 2. So next thing Mr. Kulik's going to do, he's going to FOIL this guy out. Mr. Kulik can do this in his head because he's a baller like that. He knows the binomial formula, or the binomial expansion, because he knows Pascal's triangle, right? AP Stats people, Can feel me with the Pascal's triangle and binomial expansion? Oh, come on, guys.
I don't remember that class.
All right. So, combine some like terms here. X cubes can cancel. X's can cancel. What do you notice about everything that's left? They all contain a factor of H. And now that I've canceled the H from the denominator, what can I do? Direct substitution. And I'm done. So, what this, yes, Taylor?
You want to do that last part you just did?
The direct substitution?
Yeah.
So I plug 0 in for H's. So this goes away, this
Okay.
goes away, and I'm just left with the first and the last.
Sorry,
That's okay.
I missed the H. 0.
Yeah, no problem. So let's just look at these two functions. Oops. Actually, let's do this. Okay. So there's my function f of x. There's my function g of x. Let's just move that in a little bit. Okay. All right. We are stopping here. Does anybody have questions for me before the weekend?
Thank you, Mr. Cross.